So in this video, we're going to solve this problem that's asking us, what is the free energy change for the reaction shown, here's our reaction, at 875 degrees Celsius if the mixture of each gas is, if we have present 0.1 mole of each gas in a 5-liter vessel. So let's think about how we are going to go about solving this equation. So first of all, we're told what is the free energy change. So what are we looking for right off the bat? Free energy change. So we're looking for delta G. We can think about our equations for delta G. So we're going to say delta G is going to be equal to delta G naught plus RT ln of Q. So now we can think about what do we know for this equation. We're trying to find delta G. So delta G is what we're looking for. So what do we know? Delta G naught is given to us in the problem, right? So that's this 33 kilojoules per mole. We know R is the universal gas constant. We just have to watch our units on this, 8.314 joules per mole times Kelvin. Temperature is given as 875 degrees Celsius. We need to convert that to Kelvin, so we're going to add 273 to our temperature. So that's going to end up being 1148 Kelvin. And natural log of Q, or Q, we have to find first. I'll just put find first. And once we have the natural log of Q, we can plug into our expression and solve for delta G. So let's find Q. So let's start off and we'll write an expression of Q. So we know Q is going to be products over reactants. So we're going to take the concentration of nitrogen times the concentration of hydrogen to the third power divided by the concentration of NH3 squared, right? So products over reactants. And now what we need to do is fill in our concentrations. Now when we do this, we have to think about what are the concentrations of everything. And what we're told is we have 0.1 moles of each gas in a 5-liter vessel. So the concentration of all of our gases are going to be the same, and the concentrations are going to be equal to 0.1 mole over 5.0 liters. So when I did that out, I got 0.02 molar. And that's going to be the same of every gas. So what we can now do is come down and calculate Q. And so Q is going to be for nitrogen 0.02 times hydrogen 0.02 cubed divided by ammonia 0.02 squared. So you can simplify this expression. You have 0.02 to the fourth on the top and 0.02 squared on the bottom. And it simplifies to 0.02 squared. Put it in your calculator and say 0.0004 is Q. Now that we have Q, we can come over to our expression. So I'm going to rewrite my equation. I'm going to start plugging things in. So we know delta G is equal to, now we have to be a little careful of units here. Notice delta G naught is in kilojoules per mole and R is in joules per mole. So we do have to be careful to convert one of our units. I'm going to switch this to 33,000 joules per mole plus, and now we have R 8.314 joules per mole times Kelvin times our temperature of 1148 Kelvin times the natural log of 0.0004. Now we can make sure units cross out, and we have our kelvins are going to go with kelvins, and both units are going to be in joules per mole. And so we can plug all this into our calculator, and we're going to get delta G is equal to negative 40 2 kilojoules per mole. So I went back to kilojoules in the end. So here's our final answer. And we can also indicate that under these conditions, our reaction is spontaneous.